I get that the ratio is 10 to the 36. Who agrees with me? Oh, about 32% of you, a third of you. Well, you can see that when you punch in these big numbers in the calculator, you can get lots of anxiety. Pardon me? Oh, 10 to the, sorry. The electric force is a lot bigger than the gravitational force. So the ratio of the electric to gravitational force is 10 to the 36th in this case. Okay? That's what I get anyway. Okay, we'll go on. You should try it on your own again. One of the problems with these formulas and all these exponents and everything is easy to make a mistake on your calculator. So try it again if you didn't get it right. Okay, so let's do it. Let's assume that we have these two charges, Q1 and Q2, and we're going to consider the force on Q2 to be due to Q1, the electric field created by Q1. After all, this is action at a distance, so there must be something happening outside it, and we call that the electric field. Now we know that F is Q times the electric field, so we can take our force law using the unit vector here, r hat, and just separate that part out. So it's Q times this thing is the electric field. E is kq1 over r squared in the r hat direction. What do we mean by r hat? It's just a direction that points away from Q1. So wherever Q1 is and wherever you are, r hat is pointing away from it. It's just a unit vector pointing away. That's all that means. There's no cancellation of r and r squared here. I'm going to keep emphasizing that. That little hat really means something. It means it's a vector quantity. It means it doesn't carry any units at all. No meters or anything. Okay? So that's our electric field. It's just what we would call a radial electric field. Radial meaning it points in the radial direction. Now it's dropping off. The strength of it is dropping off like 1 over r squared. And you recall that with a point source of waves, as you got further and further away from a point source of waves, the intensity of those, the amount of energy per unit area carried by the wave was also dropping as 1 over r squared. This is sort of a feature of three-dimensional geometry, that things like this drop with 1 over r squared. Works for gravity, works for electric fields, maybe it works for everything. Well, as it turns out, not. It doesn't work for the forces holding the quarks together in a proton, for example. That's a force that increases with distance. Very bizarre, inside-out world sort of thing. So there we are. We think of this point charge as creating an electric field and pushing Q2 away. Now, you ask yourself, well, why do you put the field on one of them but not this one? Well, because we're talking about the force on Q2. If we were talking about the force on Q1, we'd think about the field created by Q2 and do exactly the opposite thing, right? Okay. Doesn't this charge feel an electric field due to itself? Well, the answer is no, it doesn't. It doesn't feel its own field. It's not, it's there at the center. If you think about it, at the center here, there is no field because it's pointing outward in all directions. There's no net direction for the field to have, so it can't feel itself. But what if we take two charges and put them together? All right? If we have an electric field from this positive charge here pointing outward, and let's demonstrate that, by the way, that the field lines radiate away from a charge. And we're going to do that by charging up this big metal sphere here. And I don't think there's any charge on it right now. I can tap it to ground. And this is called a Van de Graaff generator. And when you turn on a Van de Graaff generator, this belt here acts sort of like the fur did on the rod, only we're taking charge from down here and putting it up there. As you'll see, that top gets charged up greatly. It's actually getting negatively charged because it's easy to move electrons around. Now when we do that, all these little hairs here, now we often do this in class with people. You can find a girl with long hair and have her touch that, but we find that they get zapped too much, and also if there's too much conditioner in your hair, then it doesn't, one of the things about hair conditioner is to keep it from being flyaway, right? And it gets flyaway when it gets charged up. One way your hair gets charged up, by the way, is to walk outside on a sunny day. The sun shining on your hair will charge it up, unless you have conditioner. Conditioner is electrically conductive and lets the charge go away. It lets it neutralize. Anyway, as you can see, this thing is slowly, charge is leaking off, but all those hairs are pointing outward, away from the concentration of charge there. Now, when we take the charge away, you can see that it'll, nice big spark. So we discharge this thing, then we make the electric field go to 0 too. So the charge spread itself out on the hair and on that metal ball at the top of the Van de Graaff. And because positive charges repel each other, it did that. But it gives you a kind of visual effect for how two positive charges look. Now, when we had the two little pith balls charged up here, you could ask, well, what does the electric field look like in between those two balls? Charge this up again. There we go. They wind around each other, but now, well, we got a little bit of charge on there. They're pushing each other apart. So here's sort of a picture of what that might look like. They each have their own electric field, and we're adding them together now. Okay, so when you have two vector fields, superposition principle says you can just add them vectorially together, and you get this. It's like the field lines are pushing each other away, almost. But really, this just results from adding together the magnitudes and directions of the electric fields. So let's talk about some of the special points on this diagram. What about the point halfway in between these two positive charges? Well, if you had brought in a test charge and asked what would be the force on a test charge right there where the red dot is, it would be 0, right? Because there'd be equal forces from each charge to the left and to the right. So it must be that the electric field right at that point is 0. Now, how do you represent that with these field lines? I don't know. We represent the electric field as radiating out from a positive charge, like so, in all directions. And by the way, it's not just radiating in the plane of, keep knocking that out, doesn't just radiate away in the plane of the screen here. It's radiating out in 3 dimensions, all at the same time. Now, what about in the vertical direction here? What if we think about the line, the plane, if you will, in between the 2-point charges? Well, at this point, let's say, there's a force from this charge up and to the left. There's a force from this charge up and to the right. And those two in the horizontal direction cancel, leaving you just a vertical component of the electric field. So the electric field is vertical, pointing up here, and underneath, it points down. And everywhere else you see here, you can see that the net force over here is stronger from this one, and there's a bit of a force from this one further away, weighted by 1 over r squared. That's why it sort of pushes the field line away from here. Now, if we could draw this in 3 dimensions, like I say, you would see that there's a whole sheet. You can imagine in between the two charges there's a plane, right? And the field pushes away, or it points outward from the line connecting the two charges everywhere on that sheet. A little bit tough to visualize in 3 dimensions, but you should begin to try, because we definitely have 3 dimensions to deal with. So let's see if you've understood that. And this is a surprisingly difficult question, as it turns out, in my experience. So what's the direction of the force on the test charge shown in the picture? Now that test charge is the red one, and it's a negative charge, and it's along that line in between the two charges, but it's slightly below. It's not at the 0 point. That would give you no force. So E is not the correct answer. Go ahead and talk to each other. Try to figure out what is the correct answer.